Picture with me, you are moving into your brand new house. You have spent months saving up for the deposit to buy land. You've argued with the contractors, with the lawyers, with the builders, with everyone. You've been hunting for knickknacks online, and you've been getting just the right furniture that fits in every room. You have a couple of friends over, or family, or just by yourself, whichever you prefer, and you celebrate this new milestone in your life. You go to bed in the evening, very exhausted, you rest very well, and you wake up refreshed, ready to try out your new games room. Just to find out that, apart from the bed you were on and the sheets you were under, you have been robbed blind. How did this happen? You rush to your new CCTV cameras, eager to catch the criminals in the act, seeing if there is something you can send to the police. Maybe they can help you get your stuff back. On the cameras, you find the footage. You see exactly what happened. But it doesn't look like there's some big criminal organization out to get you. You see the pickup truck pull up to the front of the gate. Someone climbs out and slides it over effortlessly. How is that possible? Oh wait, the guy who installed the gate motor only had one receiver, and that was giving issues. So he had to go to the warehouse to get another one, and he was going to bring it back today. So you just kept the gate on manual in the meantime. Okay, you see them pull into the driveway. They walk up to the front door, unlock it, walk in, open the garage, and carry everything out. How did they get access to that? Oh, you were out of town for a couple of weeks, so you gave a key to one of the contractors, just so they could finish up what they were doing. You didn't want to hold up construction. But why didn't the alarm go off? Or maybe you forgot to activate it yesterday, or you bypassed the front door for some reason. Now, you wouldn't secure your house like this. But what about your app? Let's imagine you have an app. It is the greatest app. Everyone is talking about your app, and everyone is using your app. Stocks are going up. You are getting some of that sweet venture capital. Meta or Alphabet are going to buy you out eventually. You get an email. It's not from Meta. It's someone from the internet. They've got all your user data. They're going to use it or abuse it unless you give them some of that sweet venture capital. You get everyone from every team that you know of. The SRE team, the platform team, security team, development team, all of them into a big war room. They have to find out, how did this happen? A while later, after their investigations are done, they tell you. Your app calls a certain endpoint, /user, /ID, /data. And someone just passed in 1 million IDs until they got all the data they wanted. But how did they get that endpoint? All your traffic is encrypted, right? Oh wait, you're using 2 different domains, one for static content and then one for API content. Now, the API content one, there were some WAF issues and you had to get to POC live that week. So while they were sorting it out, you just ignored certificate errors. The fix is in source, but it's only going next week. Okay, but how did they pass in all those IDs? Shouldn't the calls be authorized? Well, the backend trusts that the API gateway did the authorization. So with that one valid user, they were able to get all the information they needed. Now, you're probably not going to get bought out by Meta anymore. And you can't even go on LinkedIn to find a job because all the IPs have been marked as part of a botnet. Now let's stop pretending and imagining, because this happens, and stuff like it happens. It sounds silly and preventable when you say it out loud, but it still happens. Hi, my name is Stephan. I'm a platform engineer at BBD. I've been on the compromised and compromising end of applications, and I'd like to talk with you today about how we can build secure apps from scratch. So first we need to look at, what is this actual app? What is it doing? What kind of data is it handling? It's much easier to defend against a threat if we know what that threat is. Now, there are different kinds of threats and different kinds of protections for these, and we need to know what they are. Are we protecting users from each other? Are we protecting our infrastructure from a malicious actor? We also need to know what the app is not supposed to be doing. A lot of times, we assume that this is knowledge shared by everyone, but not everyone is always working from the same assumptions. So it's best to be explicit about these things. Is one user supposed to be able to access another user's data? If not, that should be an explicit requirement, and we should test for it. We need to look at our supply chain and engineering for the problem that we have. We need to look at the stuff we're pulling into the project. Is it too much? Is it too little? Or is it just right? We need to look at the frameworks and the tools we are using. Frameworks and libraries are very helpful, but they often are very opinionated, and they don't always have secure defaults. What might work for one company or product might not always work for our companies and our products. An example of a family of libraries that always get imported into projects but aren't really needed is the is-even and is-odd series of NPM packages. If we look at is-even, we see all it's doing is importing is-odd and returning the inverse of that. If we look at the is-odd package, we see there's a lot of files and a lot of code, but all it's really doing is a modulus 2 and checking if the remainder is 0. There's no reason for us to import third-party libraries just to do this function. We can do it ourselves. We'll have more auditable code. Sure, we need to write helper functions every now and again, but if we look at the definitions, we see that taking out white space, the inline code is actually shorter than having the helpers. We should never trust user input if we accept any user input at all. Malicious actors and normal users use the same interfaces to interact with our applications, and we don't know upfront if this user is malicious or not. That being said, we don't want to treat our users like criminals. Maybe someone entered the wrong password because they're trying to compromise your infrastructure. Maybe the user just really forgot their password. They're not using a password manager for some reason. So instead of blocking the IP outright, we can just add a small rate limit to it. An attacker is going to be immensely frustrated by an extra 100 milliseconds on each call, but a user is not going to notice it. We should also not depend on obscurity. Obscurity is at best a temporary defense. The cryptography that keeps stuff like our banking transactions safe, they are all public. And despite this, no one has been able to find a way around it. Even if someone does find a way around this, or we make advances in compute power, we have ways of making this much more difficult again. Your code should still be secure, even if the entire code base is on GitHub. And if you're using third-party libraries like Swagger or Express, it is. Now, this might sound a lot like shift left or DevSecOps. It boils down to you build it, you secure it. The developer should be the most intimately familiar with what the code can or cannot do. Even if the business rules are a bit hazy, there should be a predictable set of outputs for every set of inputs. Now, it's great to have a security team. It's great to have people who can guide you along this journey, who can recommend tools, who can help you with investigations. But they're not always necessarily familiar with the business rules or why you did things in a certain way or what the code might actually do. So let's have a look at an actual app. How might this manifest? If we look at the high-level flow for this, a user is going to send a request to the front end. The front end is going to serve some static content, HTML page. On this HTML page, the user can add a name, a password, and a number and send it to the backend. The backend will verify the credentials, store the user and their query in a database, and return some stats about the number that has been input. There's also going to be an endpoint for historical queries, which the backend will return to the user. Now, you might be wondering if we're going to be using the latest and greatest frameworks for this, but we're not. We're going to keep it simple and engineer for the specific use case that we have. In this case, jQuery, pure CSS, and vanilla node.js will be all we need for this project. Now, what are some of the threats we might face with this specific application? Well, first up is DDoS, or distributed denial of service attack. This happens when a bunch of machines from all across the world target your app, and they get you to serve requests. The attack works if you're serving more malicious traffic than you are serving actual users. Next up is the EDOS attack, or economic denial of service. Now, if we run into something like a DDoS and we don't have adequate protections, we might run up a massive bill. This is especially true in cloud computing. We pay for data egress and we pay for EC2 instances that we spin up. If we don't have proper protections in place, it can do real financial harm to the company, and we haven't even served any actual users. Next up, we need to look at our supply chain. We need to look at everything we're installing into the project. It doesn't help we are we have a very secure front end, but we're installing the vulnerability as part of our CI/CD pipeline. We need to, again, look for malicious data that's coming in. This could be in the form of a SQL injection attack, someone trying to do cross-site scripting, or someone just feeding garbage data to the program in order to try and break it. We also need to think about resource exhaustion attacks. Because our code is public, someone might be able to see that we insert queries into a database. So what they can do is they can just spam us with insert until the database runs out of space. Now we might have an ops team or some monitoring setup that tells us about this, but we can also set up technical controls. In our case, we have a control that's set up that is going to drop users over a certain date, so we limit the amount of data available in the database at any given time. Now this might again be exploited by an attacker who knows of this mechanism. They can just keep sending us garbage data, so we drop all the valid data from normal users. Now, in our case, the storing of the data isn't on the critical path of the app, so it's a risk we can accept. What other mitigations can we do apart from just the design? So we can add Nginx in front of node.js. Nginx is a purpose-built reverse proxy. It has access to a lot more processing power than node.js does, and it'll help us filter out the bad traffic before it goes to Node. It also has built-in rate limiting capabilities, so we don't need to worry about installing extra things and where they might come from. Something else we might need for the app is a logger. We want to know, did something go wrong or did something not go wrong? And we want to log those queries. Now, something like Winston or Bunyan spring to mind, and we can install that. But in our case, we're just going to write the logger ourselves, because we know what it's doing and where it fits into the app. We can make our code more audible and more secure by writing the stuff ourselves. I wouldn't normally recommend this for production use, but we are doing it here to illustrate the point. Our logger is now immune from supply chain attacks. We also don't have to worry about a new version breaking anything, because we're in full control of the code. We might need to handle dates in some sense. Now, it's tempting to import moment.js, but unless we're talking across time zones or we need to do some fancy math across dates, we can really just use vanilla JavaScript dates. For our HTTP framework, we are going to be using Express. Now, we can write our own. The RFC for HTTP is public, after all. But we're not going to do it in this case. There's a lot that's not under our control from the user side. We don't know what machine they're using. We don't know what browser they're using. The Express framework helps abstract that away from us and helps us focus on the problem at hand. If it wasn't doing that, we would write it ourselves, or we would just use something else. Now, this might be true for the logger as well, but it's much, much easier to mess up an HTTP web server than it is to mess up a console.log statement. We'll also be writing our own math functions, but we will not do our own cryptography for the same reason that we don't do our own HTTP web server. It's very easy to mess up, and it might look secure, but it might be very easy for even the most basic mathematician to get past it. Some additional things we might need in our project would be a makefile and a Docker file. The makefile helps make sure that what we're doing locally is the same thing that the CI/CD pipeline is doing, is the same thing as another dev on their machine is doing. Docker helps again make sure that the stuff we've installed is the stuff that's running on CI/CD pipeline, is the stuff that's running in prod. It also helps with process and file system isolation. Now, we can put all of this in a README file, but developers have been known to skip over arbitrary sections in README files and also copy and paste stuff wrong. Let's look at some actual source code to see what we are passing to the user and how we've set this up. We can see the HTML page coming back here. Now, there's 3 sections that we can pay attention to. The first is the set of instructions here. Then we've got a section for the user input, and we've got a section for the user output, just before our small imports. A thing to note here is the password field is of type password. This masks the input on the page. This helps protect against shoulder surfers and people watching your screen share. If you're using OneNote or Notepad++ to store your password, please also be aware that everyone can see the password you are copying from there. So please use a password manager. If we look at the app.js file we're importing, we see we've got this getAuth header function. It takes the username and password and puts it in the basic auth format. Note that this isn't secure if we're not using HTTPS, so please always encrypt all of your traffic. In the next section, we've got validators. We'd like to make sure that the name the user passes us is only alphanum characters, and the number that's coming through is actually just a number. Now this is to nudge the user in the right direction, but a malicious actor can send the stuff directly to the server. So it's important that we add server-side validation as well. If we look at our submit button handler, we'll see it's taking the name and the number from the page. We're posting it to API stats, adding our authorization header, and adding the object we've defined earlier. From the data we're getting back, we are looping over it and adding it to the HTML page for the user to see. Now this content is coming from somewhere. It's coming from Nginx. So let's look at the Docker file that we have for that. We are using the official upstream for Nginx, copying over our static files, our site config, and our certificates that we've made for our encryption. If we look at the configuration file that we've copied in for Nginx, we'll see there's a lot going on here, but we can walk through it. At the top, we've got a red directive, which tells it to limit the IP address to 4 requests a second. This should be more than enough for us to get the static content and to make some API requests. Next, we can see we're listening on port 443, or the HTTPS port. We're defining the certificates that we've copied over and defining the server name. Then we've got 2 location blocks. The first is the API block. We can see we're using the directive defined earlier to rate limit these requests with a small burst if someone did actually want more API requests done during that second. We've also got a small block to check for authorization, and we're throwing everything out that doesn't have it. All our API requests need to be authenticated, so this is stripping out the bad traffic so that Node.js can only focus on the good ones. We're rewriting the path slightly to take out API, and then we're passing it to the backend. Our last location block also uses the directive we've defined at the top, and it's just serving the static content from the file system. The backend, which is Node.js, the Docker file looks similar. We are using the official upstream image, copying in our package JSON, and installing production-only dependencies. Now we do this here to avoid issues with different architectures or different versions that might slip in between the CI/CD pipeline, your local machine, and the eventual target. Then we're copying in our application code, and the command we will run is npm run start. Looking at our package JSON, we'll see our main file is index.js, which we'll look at shortly, and we've got minimal dependencies, only basically those we've discussed. We've got some extra dev dependencies just so we are able to test our code. If we look at this index.js, at the top level imports, we'll see we have very, very little requires. We've got the 2 we've basically spoke of, which is Express and one of its modules, body parser, just to help us parse the content. And all the other requires are local, for libraries that we wrote ourselves. First up is the logger. We can see the logger is actually a very simple object. It's got a level field, which tells us which level we're on now. There's a levels field, which is an enum of all the available levels and a numeric representation for them. Then we've got a do-log function, which handles the meat of the request. It's iterating over its arguments, stringifying them, adding a timestamp if it's not there, and doing a console.log. There's a function, canIlog. It checks if the current level is acceptable for us to log at. Then we've got the named functions, like info, error, and warn. They check if the level we're at is appropriate for logging this specific one, and then it invokes the do-log function. Astute readers might note that our stringify is in a try-catch block. This is to avoid cyclical dependencies when logging. Now, this normally happens when someone dumps the entire request object. But if you really like your ops team, please don't do this. The people supporting your app will have a much better time if you log specifically what you need and what went wrong instead of the data of the entire application at that specific time. We've also got our little config import here. And these are variables that we can use across the project, sort of like globals, if you will. Now, if we're managing different environments like dev, QA, and prod, or your local, we can set specific overrides with process environment variables. We also have access to the file system here, so we can import files if necessary. Looking at the main stats function, which we're calling from the front end, let's see what's going on here. First up, we'll see we're taking name and number directly from the body, explicitly. Now we can just take the entire request body and pass it around, but this could open us up to prototype pollution. This is something especially to be aware of if you're using any kind of templating engine. Next, we are sanitizing these values. Again, the name should be just valid name characters, and the number should be valid numbers. Someone might be passing this directly to the server, so we are double checking it here. From there, we are checking if the user is a special anonymous user. If not, we're adding the query to the database. And then we're sending some stats back to the user. Now, what does this stats function do? Well, this stats function checks is the number even or odd. But we're doing this with our own helper that we wrote. No need for any third-party dependencies here. Based on the return of that, we're returning some stats. If it's odd or even, we are returning different things. Let's look at the math functions we use in here. We've got our max function, which returns the greatest of two integers. We've got our isEven helper, which is the modulus 2, checking for remainder 0. And then we've got a naive numpowers function. This just shows the power of a specific number. We've got name hashing, a greater num, and a lesser num functions. And hopefully these are self-explanatory. Looking at our database helper, we see a very similar structure. We have very minimal imports, and then we've got our own local libraries. And we are initiating a new database based on the config. If we look at the check user function, where we look at the database, we'll see some important things going on here. First of all, we create a hash from the password. We never store passwords in clear text. This is in case the database does get leaked somehow. An attacker can't just view someone's password. We're also adding something at the front, in this case the username. Now, salts and one-time pads are used to make sure that even if the database does get leaked, someone can't run a rainbow table attack against it and check for passwords. This also helps against curious database administrators who want to see if someone maybe shares a password with them. Next up, we've got add query, add user, and get user queries helpers. A couple of things to note that we're doing here. First off, we're parameterizing our data. This makes sure that the values we insert into specific columns stay in those specific columns. We don't build up our strings from scratch in case someone might be able to SQL inject us. Next, we're getting specific fields and only what we need from the database. This helps for code auditability to make sure we know what we're getting from the database, we know where it's being used. This also helps prevent data leakage in case someone is able to pull off a SQL injection attack. Looking at our cleanup function that we spoke about earlier, we can see there's not much going on here. And while this query might work, this is very inefficient if we're going to start running against large data sets. So then we might need to refactor this a bit. Now, I've tested all this code, and I'm sure it works. You'll just have to trust me on that. But I've also written unit tests. We need our testing to be automated to make sure that it stays working. It might be that one day we forget about an obscure test case. Unit testing helps make sure that we don't forget about those. Or if we transfer to a new developer, they don't need to remember those. They can see it directly from the code. So now we've taken great care in making sure what's in our code, what's coming in, and what is there. But let's look at some things that somehow still made it in. The first questionable dependency that made it in is this module has. Now, this is the entire source code for it. We can probably write this on our own when we need it. There's no need for a third-party library import. Some other things that made it in, the IP and the IP address projects. Now, these look quite complicated, and they're handling a complex topic. So it might be best to use a framework or a library for this and not to write it ourselves. But let's look at the GitHub pages for these. We'll see that the IP project hasn't been updated in quite some time. Now, this might not be a problem. If the software is stable and it works, then it works. But if we look at the issues and pull requests, we see there are a bunch open, and they don't have a lot of interaction on them. This means that if we ever do need support for this project, we are on our own. Looking at the IP address project, which does the same thing, we see that there was a recent update, which is a good thing. It means someone's working on it. But if we look at the pull request and features again, we'll see that they are looking for a new maintainer. Now this means the long-term support of this project is in question, but it could still go either way. Now, we've only got 3 explicit prod dependencies, but somehow we've got over 100 indirect dependencies. And now I know it's not everyone's idea of a good time to comb through all of these dependencies over a weekend to see what's coming into the project or not, but we're basically trusting these single 3 projects now, that they will always audit their code, that they will not have insecure dependencies, and that they will not be breaking anything once there's a version update. Now, why do we keep hammering on about dependencies? Well, let's talk about some recent incidents. The first one is the Apache log4j exploit log4shell. Now, this vulnerability had existed since 2013, but it was only exploited in the wild late 2021. And great chaos ensued at a lot of corporates to try and get this dependency patched. Now, for your project, going from version 1 to 2 might be quite easy. But if you have 100 dependencies that also need to do this, it's a very, very different task. And if you don't have stuff like automated builds and automated testing in place, your operations team is not going to have a fuzzy feeling about taking this thing to production, even if it does fix a security issue. Next up is the event stream incident. Now, event stream was quite a popular library, over 2 million weekly downloads. Even so, the original code had not been updated by its owner, Dominic Tarr, since 2012. In late 2018, he gave over to a new maintainer, a user called Write9Control. Now, Write9Control turned out to be a malicious actor. They added a new dependency to event stream called flatmapstream. A few days later, we don't know who, but someone introduced a vulnerability into flatmapstream. When event stream updated, it got the vulnerability. And if you depended on event stream during this time, you also got the vulnerability. Okay, but what does this vulnerability actually do? Well, it looks for cryptocurrency stuff on your machine, and then it ships off your wallet and your key somewhere, and they transfer the funds to an account they own. Now, luckily for most people, there were a set of conditions that had to be met for this to happen. First, you had to be doing a release build. You had to be using the Copay application, and you had to have more than 10 Bitcoin in your wallet before they would do the transfer. Now, these sound very exotic, but these exploits are known to happen in the wild. We have email validators that steal SSH keys and other C2 data, and we have GCC compiler helpers that run crypto miners while they're compiling. Okay, so that was a lot of info to take in and a lot that can happen. And we're not even building apps from scratch. We've got existing code bases. How do we secure those? Well, we can look at the same principles and just walk through them. Firstly, what is your application doing? Is it supposed to be doing that? Is it doing anything that it's not explicitly supposed to do? Have we defined all of these, and do we test for them? What are the threats we're facing? Have we clearly identified them? Where are the boundaries for things we can secure and that we are responsible for? What are the dependencies and tools we are using? Do we understand our frameworks and their dependencies and assumptions? Are we bringing in stuff we don't really need? Are we using the right tools for the job? Who are we trusting? Are we checking all of our inputs? And which systems do we trust, and why? Can small things bring us big security benefits? The code we walked through today is available on GitHub if anybody would like to review or have a go at it. If you are looking for more, search is your friend, but feel free to reach out as well. Secure by design and defensive programming are things to look out for. I hope you've enjoyed this talk, and thanks for watching.